Hello there. After the introductory video on logarithmic functions, the base E, we're now ready to try a few worked examples. So here's I'm going to go through two actually. So here's our first one. Have a read of that and we'll go through it together. Alright, the x-intercept. Well, there's nothing new about finding an x-intercept. You let the function equal 0. So when we do that, we can say 0 equals 3 ln x plus 4 minus 2, and we can add 2 to both sides and divide both sides by 3, so we get 2/3 equals ln x plus 4. Now what we do is we exponentiate both sides to find that e to the power of 2 on 3 equals x plus 4. Therefore, x equals e to the power on 2 over 3 minus 4. Okay, so that's our x-intercept, which we should in fact write as an x-coordinate, and also approximately we could note that it equals negative 2.1. So let's just write it like that. Negative 2.1, that's an approximation of course, 0. Okay, so that's our x-intercept done. Let's have a look at our y-intercept, and not surprisingly we're going to let x equal 0. So when that happens, what we get is fx equaling 3 ln, now x is 0, so it's just ln 4 minus 2, and that is actually our what I call the y-intercept, but it's really the function axis intercept. We can again write that as a coordinate, and for plotting purposes it would be helpful to have an approximation, and if you use your calculator you're going to find that that is equal to 0, approximately 2.2, good enough for our purposes. Okay, the asymptote. Well, the asymptote, let's go back to our original function. The asymptote is going to occur when the argument of the log function, by argument I mean what's in brackets here, is equal to 0, because ln 0 is undefined. So we simply say that. We say let x plus 4 equal 0 in this case, therefore x equals negative 4. Okay, so we've got a vertical asymptote at x equals negative 4. There's another convenient point to be plotted if we want, and I do want, and that is where the argument here is equal to 1. Why is that? Well, it's because ln 1, in fact log any base 1 is going to equal 0, isn't it? So that's rather convenient. So letting x plus 4 equals 1, let x plus 4 equals 1, we get x equaling negative 3. And what's the value of the function when x is equal to negative 3? Well, negative 3 plus 4 is 1, of course, so that's ln 1, which is 0, so the function value will be negative 2. So that's another cheap, easy point that's going to help us plot out a sketch of our function. So let's just do it like that, negative 3, negative 2. Okay, what's our domain? Well, the the asymptote is going to tell us a lot about the domain. The asymptote happened at x equals negative 4, and it turns out that everything less than x equals negative 4 is going to be in our domain. The range as per usual is all real numbers, and I like to use interval notation to indicate that the range is between negative infinity and infinity, not inclusive. So I may have said it earlier that the domain's less than -4. It is, of course, as written here, greater than -4, which is quite easily seen. If you look back at the original function, we need everything in here to be positive. So it's positive as long as x is greater than -4. Now the other thing we should do is have a general idea of what our plot looks like before we start plotting it. And by that I'm talking about the general shape of it. Now looking here, we see that the coefficient of the log function is positive, and what's in brackets there, well, the x is positive. So it's going to follow the general shape of the basic log function. This one I'm tracing out here. Okay, it's going to rise from left to right, and like this one here, and it's just being shifted around the number plane a bit. So this is what it does in fact look like, and notice what I've got plotted: the y-intercept, the x-intercept there, e to the power of 2/3 minus 4. You can use the approximations if you prefer. Here we've got what I call the convenient point. There's my asymptote at x equals -4, and as you can see, this bears out the idea that the domain is any value, well, x is greater than -4. And the domain is, sorry, the range is the set of real numbers from -infinity down that away to positive infinity, because this is increasing without bounds, albeit very slowly up around here. So it's increasing up to approaching infinity. Now let's have a look at our second example. Fx equals -0.5 ln 2 minus x in brackets plus 1. Might be an idea to get we left this to last in the previous example, but we can get an idea of what this is broadly, the shape of the graph anyway. Notice the coefficient of the log function is negative, it's -0.5, and what's going on here is that the x within the argument here, that's also negative. So looking at our earlier sketches, we can see that we're looking at a graph of this shape where the coefficient of the log function is negative, and the sign of x within the argument is also negative. So it's going to rise from left to right. Okay, so let's have a dig at this one. So it's the same procedure. These are quite routine, these. So to find the x-intercept, you're going to let the function equal 0. So when that happens, we get 0 equaling -0.5 ln 2 minus x plus 1. Therefore, -1, and I'm going to do two moves in one go. Divide both sides by -0.5, divided by -0.5 is equaling ln bracket 2 minus x. Okay, so what we will do now is exponentiate both sides, and also -1 divided by -1/2. Well, two negatives makes a positive, and 1 divided by 1/2 is the same as timesing by 2, isn't it? So we can say 2 is equal to ln 2 minus x. Exponentiating both sides, we get e to the power of 2, or e squared, equals 2 minus x. Therefore, x equals e squared. Oops, this isn't going too well. Sorry, I should say 2 minus e squared. Okay, now if you want a numeric approximation, I think you're going to find that it's equal to about -5.4. So let's indicate our x-intercept as -5.4 approximately, of course, comma 0. So that's an important point. Now the y-intercept, we're going to let x equal 0, of course. So that occurs at fx. I keep saying y-intercept, don't I? But I mean the function axis intercept. We're letting it equal 0, so it's equal to 0.5 ln2 plus 1, and that's approximately equal to 0. Actually, it's very close to 1 in fact, so approximation only, of course, 0, approximately 1. Okay, the asymptote. Now we know what to do there. We let what's in brackets here, 2 minus x equals 0. So the asymptote is obviously going to be at where x is equal to 2. Now we can pick another convenient point, and that's going to be where our what's in here equals 1. Why is that? Because, well, ln 1 is going to equal 0, and then negative 0.5 times 0, 0 plus 1 will give me an easy point to plot. So let's just note that down, and we can say let 2 minus x equal 1, therefore x equals 1. Now when x equals 1, our function is going to equal negative 0.5 times 0, 0 plus 1, and that equals 1. So we've got another convenient point to plot at 1, 1. So that'll help us get the general shape of the plot. Okay. Now the domain, well, what's helping us there is the asymptote. That's x equals 2, you can see that. So if we look at our function back here, we can see that x has got to be less than 2, doesn't it? As long as it's less than 2, we are going to have a positive value in here, so that's okay. So we just say that the domain is x has to be less than 2. The range, as is usual for a logarithmic plot using interval notation, is negative infinity to infinity, not inclusive. So recalling that our general shape is going to be of this variety because the coefficient of the log function was negative and what was in brackets here was negative as well, we end up with a plot like this. I've got my x-intercept plotted, y-intercept or function axis-intercept plotted, the asymptote is x equals 2, I've got my convenient point there and I've got it labelled, and the axes and plot has arrows on the end of it, so that should do.